Okay, this is question 6 from the SACE Stage 2 Physics Course Companion from section 1.2 Forces and Momentum. So a ball of mass 1.5 kilograms moving at a speed of 10 meters per second collides with a stationary ball which has a mass of 0.8 kilograms. After the collision, A moves off at V at an angle of 40 degrees above horizontal, and B moves off at 4 meters per second at an angle of 50 degrees below horizontal. We need to use the law of the conservation of momentum to determine the final speed and momentum of MA. So first up, we need to define what we mean by the law of the conservation of momentum. So here, the law of conservation of momentum is that in any closed system, the net change in momentum is 0, therefore the initial momentum must be equal to the final momentum of the system. So this is what we'll be using in this question. So first we need to work out the initial momentum of the system. So I'll do that over here. So here it'll be the initial momentum of A plus the initial momentum of B. So A has a mass of 1.5 and it's moving at 10 meters per second. So 1.5 times 10, and ball B is stationary, so it's got 0 momentum. Therefore, the initial momentum of the system is 15 second newtons. Now, the final momentum of the system is a little bit tricky. We have to use a vector addition. So if we draw a quick diagram, we have ball A moving up with momentum. We don't have the speed, so we can just write an expression for that as PA equals 1.5 V, and that's at 40 degrees. And ball B moves at 50 below horizontal, and we'll just draw that. We do know the values of the speed and mass of ball B, so that's 0.8 kilograms moving at 4 meters per second, so that'll be 3.2 sec newtons. Now, if we're going to add these two momenta together, we're going to use a vector addition. So it'll be the initial, so the final momentum of A plus final momentum of B. Now we have from the question, if this is 40, that'll be 50 up in that corner, and similarly, if it's 50 degrees below horizontal, this will be 40 in that angle there, so we end up getting a right angle. I'll draw that again to make it a little bit easier to see. So we have 50 plus the 40, and that'll be a right angle there. So I'll put the values on this one. So we have 1.5 V, and we have 3.2 second newtons. Now, from the law of conservation of momentum, we know the initial momentum is equal to the final momentum. So the initial momentum was just a horizontal momentum at 15 second newtons. So therefore, this must be equal to 15. Now it's just a matter of using Pythagoras' theorem to work out the value of V, because we have this right angled triangle. So from Pythagoras' theorem, we have A squared plus B squared equals C squared, so 1.5 V all squared plus 3.2 squared equals 15 squared. Now we can work out V just by rearranging this to get V on its own. So first we'll subtract the 3.2 squared from 15 squared, and that'll be equal to 1.5 squared multiplied by V squared. Therefore, V squared will be 15 squared subtract 3.2 squared, all on 1.5 squared, and finally v will just be the square root of all of that. So the algebra is a little bit tricky for this question, but not impossibly tricky, and if we substitute that into our calculators, we should get 9.77 meters per second. So from the law of the conservation of momentum and some vector addition, we've worked out the final speed v of ball A. So the hard bit is doing the vector addition over here, but by now we've probably done a few of those, so it should be okay. The final part of the question is for us to work out the momentum of ball A, the final momentum of ball A. So here we have, I think we'll just work out the magnitude. That'll be MA multiplied by VA. We've already worked out the final speed, that's the 9.77. The mass is 1.5. So this will just be 1.5 times 9.77. And if we substitute into our calculators, we should get approximately 14.7 secnewtons. And that's it. Two-dimensional conservation of momentum using vector addition. It's not too bad. After you've done a few of these, it becomes a little bit more routine, and it's likely that we're only going to encounter right-angled triangles or equilateral triangles.